Hello dear students, welcome to the channel Pen and Paper Chemistry. We'll try to make chemistry easy for you, and the only thing that you need is a pen and paper in your hand so that you can take down notes based on what we are going to do in today's lesson. So are you ready? We are continuing with our learning of diazonium salts, and we've already loaded 2 videos on the topic. Diazonium salts, the example that I am taking up today is C6H5 and triple bond N Cl negative. What is the reason for the stability of this compound? All this has been discussed in the previous video. I repeat, the preparation of benzene diazonium chloride or benzene diazonium any other ion. So for example, bisulfate nitrite. So how do we prepare this? To make things simple, we are going to concentrate on benzene diazonium chloride in this lesson. We prepare it by a diazotization. So what is diazotization? You treat aniline with nitrous acid. HNO2 is nitrous acid and concentrated HCl. A very important thing in this reaction is the ice cold reaction condition. So you carry out this reaction in a dish containing ice cubes. When you will do this in the laboratory, you will be using ice in order to carry out this reaction. Interestingly, we do not isolate the diazonium compound. Whatever reactions have to be done, we add it to this test tube. We add the reagents to the test tube directly. We do not isolate the diazonium salts because they are explosive in nature. Preparation: aniline reacted with, yes, this is aniline, an aromatic amine. Aniline is treated with nitrous acid and concentrated HCl at 0 to 5 degrees Celsius, giving us benzene diazonium chloride, water, and what else will you get? Nothing, right? Now, interestingly here, the nitrous acid that we need is a very unstable acid. You will never see a reagent bottle saying nitrous acid in the laboratory. It's very unstable. So what is done is it is generated in the reaction mixture itself, and the word that we use is in situ. So what do? Is I'll add aniline to the test tube. I will add sodium nitrite to the test tube, and I will add HCl, all three to the test tube. Now you must be wondering, where did the sodium nitrite come from? Sodium nitrite is used to generate nitrous acid in the reaction mixture. That means what we call as in situ. It's a simple double decomposition reaction, positive, negative, positive, negative. And we get the NaCl and nitrous acid here. The nitrous acid generated will react with the aniline along with HCl to give us C6H5N2 positive, Cl negative, and water. Right? So I've got my diazonium salt over here. What are the uses? What are the applications? What are the properties of this diazonium salt? Before we go ahead with that, please make sure that you have written down these reactions yourself. For those who are taking screenshots, it may not be so helpful as writing this reaction yourself. So please take time to press the pause button on this video. Write down the reaction yourself, write down the reaction conditions, and let's get going with property number 2. No, property number 1. Coming to the properties, I've divided the properties of diazonium salts into 3 categories. The first is reduction, which is done with the help of hypophosphorus acid. It is H3PO2. Okay, so this is hypophosphorus acid and not phosphoric acid. It's short of oxygen, right? That means it can be a very good reducing agent. The other is where the C6H5 positive, the phenyl group, acts as an electrophile. The third category of reactions is where the C6H5N positive triple bond N, that is the diazonium ion. The diazonium ion as a whole acts as an electrophile. And interestingly, such reactions are known as coupling reactions, and they give us very important category of dyes known as the azo dyes because of their color. Do you remember the flow chart that I gave in the previous video where we have colored these azo dyes yellow and orange? Do you recall that? So our first property here is the reduction of benzene diazonium chloride. So benzene diazonium chloride undergoes reduction on treatment with hypophosphorus acid. When we take the aqueous solution of the benzene diazonium chloride and treat it with hypophosphorus acid. Yes, aqueous solution. Why will it dissolve in water? Yes, because of the presence of ions in this. This is going to behave as an ionic compound. So what will happen is it will reduce to give us benzene, nitrogen. Can you complete this reaction? Phosphorus acid, H3PO3, and because our hypophosphorus acid, something which was short of oxygen, has got oxidized to H3PO3, and finally our product, that is HCl, right? Many a times we do write our organic reactions in the form of a skeletal equation as well. So the above reaction can also be simply written as H3PO2 and water above the arrow, and we can simply write it as C6H6. Then in that case, we do not concentrate our energies on the side product, right? But you will have to follow what your teacher tells you to do. Have you written this down? Only watching will not help. Please write the reaction. So if we connect our learning to this flow chart that I had given you, remember we had done this flow chart in the previous video. So if you've drawn this flow chart, now try writing all the reactions based on this chart. The first one has already been done. So aryl diazonium salt reacted with hypophosphorus acid gives us C6H6, nitrogen, phosphorus acid and HCl. Go on to the next one, converting aryl diazonium salts to phenol. How do you do that? Yes, you again take an aqueous solution, acidify it with dilute H2SO4 and heat it. Simple. Go ahead and write the reactions. I will also write the reactions, but it will be good if based on this flow chart you can write the reactions yourself and tally with what I am going to write. Believe me, you will feel very, very happy with yourself and the kind of confidence that you will gain at the end of it all. Go ahead, try it. The next property shows the behavior where the phenyl group acts as an electrophile, an electron loving. Phile is loving, so electron loving species. Now where do we get the C6H5 positive from? For this, just let us see the structure of the diazonium ion. Now you know that nitrogen gas prefers to be on its own. Nitrogen, with respect to carbon, has a tendency to withdraw electrons towards itself. And that is what it is going to do now, leaving phenyl alone with a positive charge and nitrogen being formed as a gas. Now this phenyl group, because it is electron deficient, it is going to behave as an electrophile or an electron loving species. That means this phenyl group will combine with anything which has a negative charge or has an excess of electrons, forming C6H5Nu. So we have basically substituted the diazo group by a nucleophile. Here the C6H5 positive group is acting as the electrophile. So let's take up the first reaction here. Can you form the products? I've written the reaction. C6H5N2 positive, Cl negative, H positive, OH negative. Replace C6H5. So what is the nucleus loving species over here? Yes, of course, OH. And there we go, C6H5OH plus nitrogen. Complete the reaction. Plus HCl, right? So I have written it in short. BDS stands for the benzene diazonium salts. Just to keep it simple, of course, this is not a standard notation. I have kept it simple so that it's easy for you to refer to it. So benzene diazonium salts getting converted into phenol. Next, introducing the Sandmeyer reaction. Sandmeyer reaction is when benzene diazonium salts are converted into chloro, bromo, cyano or hydroxyl derivatives. So we have here benzene diazonium chloride reacting with the copper halide or copper cyanide in the presence of the hydrogen halide to give us the substituted product. Go ahead. So here's our nucleophile, our first product. Please pause the video, try these reactions yourself. Go ahead, try them. Write the products. C6H5Br. C6H5. See, look at the nucleophile in each case. C6H5Cn. These are not the exact mechanisms. I am just trying to make things easy for you to remember. Now another modification of the Sandmeyer reaction which I had not put in the flow chart is where you convert it into the hydroxyl derivative. Did I write the formula correctly? No, it is C6H5OH. This is what happens when you keep talking and writing as well, right? So the last two reactions are actually not Sandmeyer reactions. Sandmeyer reactions is where you're getting the chloro and the bromo derivative. The next two reactions where you're getting the cyano derivative and the OH derivative are actually modifications or extensions of the Sandmeyer reaction. But they are giving us very interesting and important products here. Another way that we can prepare the chloro, bromo and cyano derivatives is through what we call as Gataman reaction. And here also our C6H5 positive is behaving as an electrophile. So it is the same reaction, only thing is instead of taking the copper salt, you are taking copper over here and heating the reaction mixture. So form the products. What is the nucleophile? Yes, of course, the Cl. So we will have C6H5Cl, C6H5Br, C6H5Cn. And of course, nitrogen will be formed as the side product. Right? Now, there's a very important use of this product. What is it? The benzonitrile that we have formed over here on reduction gives us an amine. So this reduces to give us CH2NH2. Partial hydrolysis, you get an amide. Yes, I can see the smile because we have already covered this under haloalkanes. Remember? COOH. So we have a carboxylic acid, COH, that's a benzoic acid, benzamide, and this will be benzyl amine, right? So you see from one benzene diazonium chloride what all products we can make. Isn't it an interesting reagent? Now that we have formed the chlorides, the bromides and the cyanides, how do we form the iodides? Let's not forget the iodides and the fluorides. You know, fluorides are much more difficult to prepare. So how do we go ahead with this conversion? Benzene diazonium salts to the corresponding iodides. Yes, of course. As you can see, benzene diazonium salt plus potassium iodide. And here again, keep things simple. What do you get here? C6H5I iodobenzene plus nitrogen plus KCl. Another interesting reaction, benzene diazonium chloride with KSH. What is KSH? In order to understand that, KOH, potassium hydroxide, right? This is what you call it as. Now, the oxide has been replaced by sulfur. Potassium still remains the same, hydrogen still remains the same. So, what will you name it as? Yes, it will be potassium hydrosulfide. Easy. Okay. Carry out the nucleophilic substitution. Remember, we did these reactions in the case of alkyl halides as well. Or did we do it somewhere else? Okay. Did you tally? Did you see the equation that I have written over here? Did you get it right? Wonderful. If you did, don't forget to pat your back. Yes. We are not there to give you that encouragement, but yes, you can give a positive affirmation to yourself. How will you name this compound? So, if you see C6H5OH is phenol. Here, the oxygen has been replaced by sulfur. So, when you have sulfur, what do you use? Yes, it's thio, right? So thiophenol. It's a phenol where the oxygen is replaced by sulfur. Benzene diazonium salts reacted with fluoroboric acid. So again, what will happen is the negative ion gets replaced and we have an interesting compound over here. And you know, yes, this is also a diazonium salt, but this is a very stable diazonium salt. It does not break down on heating. It does not explode on heating. So let us name this compound C6H5N2 positive BF4 negative. As I said, it's a very stable compound. So stable in the sense it will not explode easily. So benzene, or in some of the nomenclatures they also say it as phenyl, but we will stick to benzene because that's how we've been naming our compound. So benzene diazonium, that is N2 group, N2 positive, tetrafluoroborate. Tetra is for the 4, fluorine, borate. So benzene diazonium tetrafluoroborate or benzene diazonium fluoroborate, even that is accepted. Now, so we have a new compound here on reacting benzene diazonium chloride with fluoroboric acid. The spelling here is FLUOROBORIC acid. Now this compound is going to give us two new compounds. The fluorobenzene, which we get on heating this compound to dryness. That means you heat it to dryness and you will have C6H5F, BF3 and nitrogen. What is the name of this reaction? Have a look at it. It's the Bals-Schiemann reaction, right? Also called Bals-Schiemann reaction, different pronunciations, different places, okay? On treatment with aqueous NaNO2, sodium nitrite, again what will happen is, yes, of course, substitution by a nucleophile. So you will have over here C6H5NO2, nitrobenzene. Otherwise, are nitrobenzenes easy to form? Have you formed this earlier under reactions of benzene? Can you recall the reaction that takes place? Now, you have written so many reactions with me. Try writing the reactions for both these reactions. So, reaction 1, benzene diazonium chloride, 2, benzene diazonium fluoroborate. Second reaction, fluoroborate reacted with NaNO2. Third reaction, fluoroborate heated to dryness to give you fluorobenzene. Please write the reactions, complete them yourself and look at your register or notebook. You have made notes of benzene diazonium chloride during the course of this lesson, which you can refer to when you are offline. Isn't that good? Okay, the last reaction of this topic, C6H5N2 positive behaving as an electrophile. You remember the two beautifully colored compounds that we had, the orange dye and the yellow dye. Now what I have done is I have written the reactants like this vertically. So this is C6H5N2 positive Cl negative. C6H5N2 positive Cl negative. Reacting it with, what is this compound? Yes, this is phenol. What is the other compound? This is aniline. Now you react them, and what is interesting over here is they undergo what we call as coupling reaction. That means the two rings will couple with each other. So when we couple the two rings, what will happen is the Cl has to move out of the way. Let's take our phenol, pick it up and help it to form a bond with the nitrogen, right? And what do we get over here? So this was our phenol, but what is our final product? Now with respect to the diazo group, our OH group is, so if I am giving this as 1, 2, 3, 4 or ortho meta para. So this is para hydroxy azo, that is from the diazonium group, benzene. What was the color of this compound? And what type of compounds can be identified with this reaction? Yes, of course, it's the orange colored compound, right? And what kind of compounds are identified with this? Could you think of it? Yes, we identify phenol. We are able to test phenol in the laboratory using this reaction. Okay, try the next reaction. Again, benzene diazonium chloride, get rid of the Cl. We pick up our aniline, take it closer to the benzene diazonium salt, form a bond over here. No, it's a yellow, right? Can you name this product yourself on the basis of what we did in the previous one? Instead of the hydroxy, what group do you have over here? What is the prefix for NH2 group? Yes, it's amino. So this is para-amino azobenzene, which is what color? Yes, it is a yellow colored dye, and it helps us to identify anilines in the laboratory. Isn't it interesting? Did you like the lesson? By the way, we have not covered all the reactions which are there under benzene diazonium chloride. My focus was more on the students of grade 11 and 12 or the senior secondary students of any curriculum. If you are doing your bachelor's or your master's, you may have to refer to other textbooks in order to complete this. You just have to add a few reactions in order to make your notes complete. If you felt benefited by this lesson, request you to share this gift of knowledge with friends, classmates, or anybody whom you feel would be benefited by it. Take care, stay safe, stay healthy. See you in the next video.